You are welcome to GMAETS 41 physics class. In this class, we are going to give attention to another part of scalars and vectors. Part 4. We'll be looking at the algebra of vectors. In today's class, we are going to explore the first two algebra of vectors, where you deal with addition and subtraction of vectors. Remember, on this channel, you learn, you believe, and of course, you can always be assured that GMAETS 41 will always break this concept for you, simplifying them so that you can love them. Yes, I will always make you love your studies. So welcome once again as we look at part 4 of scalars and vectors. In our previous class, recall that we introduced vectors in 2 dimensions, where we learned how to resolve vectors into 2 dimensions when you have vector components. And we brought in the knowledge of trigonometry, for right angle triangle, where we made use of the concepts of sine theta and cos theta, the resultant multiplied by sine theta, resultant vectors multiplied by cos theta, in order to get the 2 perpendicular vectors, which can now help us to obtain the overall resultant. I want to believe that you have done justice to that class. So today we are looking at another aspect of vectors in 2 dimensions, and then we'll also talk about vectors in 3 dimensions. First of all, here we are going to deal with what we call the unit vector. When a vector is in 2 dimensions, right, that vector is said to be in plane. We explained that from our previous class. This is the origin, so you have one of the vector and you have the other vector. These 2 vectors are perpendicular because they meet at 90 degrees. We can talk about the direction of this horizontal axis, and I will use I to represent it. Let me put something like a cap here, because that's a symbol for unit vector. Then, along the other perpendicular axis, which is y, we are going to use j for it. What is the whole idea of these? The direction vector in the x-axis and the direction vector in the y-axis are represented using I and j, respectively. Remember, a vector has magnitude and direction. So our ij are the 2 symbols we use to represent the direction of the vector, okay? We refer to them actually as unit vectors or direction vectors. So we shall start first by defining the concept of unit or direction vector. Unit or direction vector. Permit me generally to use U to represent that unit vector. Let us assume that we call a vector U. So the unit vector of that vector is going to be written like this. So what is a unit vector? A unit vector is defined as a vector whose magnitude, whose modulus, whose absolute length, whose size, whose value is 1. Unit vector. A vector whose magnitude is what? 1. The word unit from English language, generally if you're translating it numerically, that's with respect to number, it means 1. So a vector whose magnitude is equal to 1 is called a unit vector. So I'm going to write something like this, this symbol represents magnitude. Magnitude of a unit vector is equal to 1. By the way, let me indicate also that this topic, which I'm introducing in physics, is also encountered in further maths. This aspect, further mathematics stretches some parts of physics. That's why some part of physics appears in further maths. Vector is one of them. Vector most specifically, okay? Good. So if you are offering further mathematics or advanced maths, you can actually meet this in your mathematics course. I've defined what a unit vector is. A unit vector is a vector whose magnitude is equal to what? 1. What is the formula for calculating unit vector? If I give you a vector now in 2 dimensions, how do you determine the unit vector associated with that given vector? Let us say given vector u. This symbol is used to represent vector. In 2 dimensions, for example, to be equal to u sub xi plus u sub yj. This means the component, scalar, this u sub x means scalar component of vector u along the x-axis. The direction is this I you are seeing. The direction is this I you are seeing. And remember I told you that we use this symbol to represent unit vector. I may not be consistent with using it always anyway, but if you are sitting for an exam and it is a question that is theory question, please try to be consistent using it. That cap symbol represents unit vector. And I told you from the beginning that this I and j you are seeing, they are actually called unit vector or direction vector. They indicate the direction of the vector along the x-axis and along the y-axis. Let me indicate x and this y. If the vector is in 3 dimensions, as you will soon see, we introduce another direction vector, which is k. Is that okay? We introduce another direction vector or unit vector, which is k. But we are dealing with the case of 2-dimensional vectors yet. The same idea we use in analyzing 2-dimensional vector, to a greater extent, we use it to also analyze 3-dimensional vector. Vector in plane and vector in space, respectively. That's what 2-dimensional vector and 3-dimensional vectors are. All right. Now, if you're given this to be a vector, the unit vector, the direction vector, which is in the direction of this given vector, is calculated using this formula. The unit vector or direction vector, the unit or direction vector, that vector that is in the direction of this given vector, the unit or direction vector is given as, so we have this formula, unit vector associated with this given vector is equal to the vector itself divided by magnitude of that vector. The vector itself divided by what? Magnitude of the vector. So if you are given any vector in 2 dimensions, it could also be in 3 dimensions. Are you following, right? This is how you calculate the unit vector. Simply divide the given vector by its magnitude. You can see that the given vector divided by magnitude of that given vector. Good enough. In our physics class previously, I've taught you how to obtain the magnitude of a vector using Pythagoras' theorem. So you are expected to memorize this formula, know about it. Are you following, right? This is the given vector. Imagine that someone gives you a vector defined as 3i plus 5j. 3i plus 5j. Calculate the unit vector associated with that given vector, or calculate the unit vector in the direction of this given vector. This is the formula you use. Remember, like I said, please, you can note it down. You can note it down, although we're going to solve questions on them. This formula you see here is also applicable to three-dimensional vectors. Okay, if it is in 3 dimension, if the vector is in 3 dimension, all we do is simply to add uzk to it. Vector in which dimension? 3 dimensions. We just add the third vector, or the third component vector of vector u. And the same formula will apply. Are you following, right? The same formula will apply. We're going to solve questions on it, even though I decided to show you, vectors in 2 dimensions instead. All right, we're going to pick a question and then solve. After which we move on to further things about algebra of vectors in 2 dimensions and 3 dimensions, to include addition and subtraction. This class we cover it. And then our next class will be talking about multiplication of vectors. Is that okay? So, take note of this equation. If you want to get the direction of the vector, you still apply that normal knowledge that we had earlier. If I want to get the direction of this vector, the angle that the vector made with positive x-axis. If I want to get the angle that the vector made with positive x-axis, all I just have to do is to apply tan theta. Permit me to draw something further here. Let us say that this is the vector u. And then you know that this vector will have 2 components. Since it is between x and y, it's going to have ux. And it's going to have what? uy. uy. It's going to have uy. Good. So it's actually from here we got this. If you want to define this vector in 2 dimensions using the component, it's going to be written like this. I actually established this in our previous class, just to show you that. ux in the direction I, uy direction j. Okay. Let's take a question. Before then, let's check the network situation before we move on. All right. You're welcome to the class. Amos Kiza, Kampana Munoswami. Amos Kiza, I don't need vector, I need money. Okay, no problem. Continue looking for money, okay? There is time for everything. Time to get money is coming. If you're a student, you need to learn. You have your developed so you can be able to face the real world. There are various ways someone can get educated. Are you following? We have the academic way where you'd have to go to school, just like you're learning now. We also have other forms of education. So if you're looking for money now, you can think otherwise for other forms of legal education. How about learning a skill? All right. So just bear it in mind that there is time for everything. You are told education is the key. Yes, education is the key to everything. I think the main idea here is for us to be aware that education is a wider concept that has different aspects. Somebody that is attending a vocational school to learn something like tailoring, to learn shoemaking, to learn massing, bricklaying, to learn hairstyling. Are you following, right? All of these are different forms of education. It's just so sad that the only thing people think about education is academic stuff, which we are doing here. This is also important because there are some people who will definitely survive from this direction academically. Others survive in another dimension of education. Well, some people might look at it and say, okay, education is a scam and other things. No, it's not education that is a scam. It's only when we think that education is only academics. That's when it now seems as if it is scam, but I don't really believe in that philosophy. Let us rather correct our idea. What is real education? Is it until somebody goes to university? No. No. So Amos, I hope I've corrected your idea. If you're looking for money, ask yourself, is it really time for you to start making money? Because yeah, there is time for everything. How old are you? That determines. Then if you think that it is time for you to make money, to start hustling, then of course, look for something that you can do. It could be a skill you learn, something legal. Take notes. For now, learn vectors, okay? Let's take our first question under this concept of unit vector. Question number 1. Question number 1. So the question we have, find the unit vector associated with f equal to 2i and f equal to 3i plus 4j. Find the unit vector associated with the given vector there, f equal to 3i plus 4j. If I assume this f to be false, for example, if I assume it to be false, that this vector is defining false vector, as this is the value of the force in x direction, this is the value of the force in y direction. It's just like you having a sketch like this. So you can say that this is 4 Newton, this is 3 Newton, and then you have the given vector here, f, right? It makes an angle here, theta. Now this is your unit vector I in x direction, that is in x axis, unit vector j in y axis. So that's just the whole idea here. To find it, so all we have to do is to apply the formula straight on. There is no big deal there. Remember, I had to show you this because an examiner has the right of giving you this diagram like this and ask you find the unit vector in the direction of this f associated with this f. Are you following, right? And so if you limit your understanding only to when the vector is given like this, you may get into trouble solving a problem like this. If the question is given in this form, all you have to do is 3i plus 4j. Then you calculate the unit vector. Of course, we have the formula of unit vector given. We have vector f to be equal to 3i plus 4j. And then unit vector f, therefore, is going to be equal to vector f itself, the given vector f, and then you divide it by the magnitude of that vector. So we know the given vector. We know it 3i plus 4j. All we have to do is to find the magnitude of that vector. What is the magnitude? Recall that from our previous class, magnitude of any given vector in 2 dimensions is equal to square root of the sum of the square of the scalar component of the vector. Every vector has a scalar in it, which are the values. So simply apply Pythagoras theorem. I've just spoken grammar. The square root of the sum of the squares of the scalar component of the vectors of the vector, right? Just forget about all of this big grammar. Just apply Pythagoras rule to this 3 and 4. Because what I'm trying to do here is simply f square equal to 3 square plus 4 square. Then to get the magnitude of f, you take square root of both sides. You see that we are going to get 3 squared plus 4 squared. And then this is going to give us square root of 25. So that the magnitude of vector f is equal to 5. So the resultant vector of these 2 vectors. Now this vector given to you is also called displacement vector. this vector given to you is also called what? Displacement vector. That's why I think is it part 1 or part 2, we actually solved the concept of displacement vector. I established a lot of things in that part 1, a lot of necessary things. So I believe that to get used to all these concepts much more, you can visit our previous class, okay? Access the lesson. Of course, subscribe to this channel if you have not done so right away, okay? Right away, click on the subscription button. And after you click on the subscription button, you would see a notification icon, a notification bell also. Click on it and select all, so that anytime I come on live or I upload any video, you will be personally notified. Okay, so we are moving on. Having obtained the magnitude, it implies that to now get our unit vector, we apply this formula. The unit vector associated with this vector f will now be, you go back to the formula, the given vector itself, which is 3i plus 4j. Then all over the magnitude of that vector, which we calculated already to be 5. This is the answer. If your examiner leaves the answer like this for you, fine. Of course, if it is a CBT exam, computer-based, or OMR sheet, you know, where you have paper given to you and you have to shade the correct option, the options will guide you to know whether to leave your answer like this or not. Most generally, though, we try to split the numerator over the denominator. So we can say that this is the same as f equal to 3 over 5i plus 4 over 5j. So this could be the answer, or this could be the answer. And observe, let me also tell you something. Look at the denominator. You notice that 5 is common to both of them. So from here, an examiner can still decide to leave the option in the format, pull out this denominator 5. So you get 1 over 5. Look at it. 1 over 5. Then open bracket, you have 3i plus 4j. This is also the same as any one of these answers. Can be written like this. And finally, let me show you something that some examiners can also do. Remember, all of these, they have the right to propose such question or options for you. So that is why you should understand the various ways in which the options to this type of question can be given. I can decide to just extract the scalar component of this vector only without showing the direction ij, without showing the unit vectors ij. So all I just have to do is 1 over 5, open bracket, 3. If I am not showing these unit vectors, these direction vectors, if you don't show them, you cannot use this sign plus there. Rather, you apply your comma, use your comma, right? So 1 over 5, 3, comma 4. Or you could still leave it as 3 over 5, comma 4 over 5. These are various ways that you present the result. These are various ways that you can present the result. So either what we have here up to this point, or you can just extract the scalar component of the final unit vector you obtained. But I select the options guide you, okay? If you are not given option, if you are not given options, then of course you may decide to stop here, or you use that format in which you factorize the denominator out while leaving the numerator there. So I want to believe that you understand this question. We have gotten the unit vector. Please let me put the cap sign. Very simple maths. Nothing is there. Are you following, right? Very simple maths. We're going to pick one more question to determine the unit vector. By the way, if I ask you to find the direction of this given vector, if it is just direction I ask you to find the direction of this vector, please take note that obtaining the direction, you would have to go directly and apply your tan inverse. tan inverse of this j component divided by this I component, which is to calculate theta equal to tan inverse. We've done this in our previous class, so it's not a new concept. I gave the formula as theta equal to tan inverse of y over x. So here the y component is 4 over the x component is 3. And then you solve this, obtain the direction. What we calculated here is called unit vector or direction vector. Like I said, unit vector or direction vector. But if you're just asked to find the direction alone, find the direction of this vector, it is theta that you are being required to calculate for, to look for. All right, let me check the network situation and if there is any question there. Amos, say, okay, well said. Thank you, sir. All right, you're welcome. Thank you for understanding what the reality is. Okay, Karpana Munoswami. The answer you got is also correct. Let me boost the network a bit. All right, so let us move on. We're going to deal with another question. This time around, I would have us calculate the value of unit vector for a three-dimensional vector. Question 2. Question 2. Calculate the unit vector in the direction plus 3j minus, let's say, 4k. How do we obtain it? You have the formula already. Simply the given vector, that displacement vector given to you, right? Divide it by the magnitude of that same vector. So solving this, all I have to do quickly without wasting time, let's go and obtain the magnitude of this vector. Magnitude of the vector 5i plus 3j minus 4k. Permit me, let us call that vector. What do you want me to use for it? Let's call it vector A. Let's call it vector A. Okay? It's not compulsory anyway. So that vector A is 5i plus 3j minus 4k. So the magnitude of vector A will now be equal to square roots. Come over to this and then sum the squares of each of them. Look at this minus 4. Anytime I'm calculating magnitude, if a number there is minus, I do not like putting the minus because to me it's a waste of time. Yes. The reason is because even if you fix minus 4 and you square it, it's automatically going to change to plus. So most times I don't like showing that minus, but let me just show it to you anyway. Minus 4 you square. Magnitude of any vector is always positive. Whenever you hear magnitude, generally magnitude is positive. So that negative there, applying it in this calculation is of no use. It's always positive. And I advise that you don't even put this negative because some of you, unfortunately, may not know how to evaluate minus 4 using certain calculators. For example, look at this calculator. If you evaluate these by pressing minus 4 and then you raise it to power 2, it will give you there about minus 16. Minus 4, look at it, then square. Look at the answer, minus 16, and that is wrong. That is wrong. So like I say, some of you may not know how to press this in the calculator, how to impute it. You see what I did here? I had to put this minus 4 in bracket before I squared it. That's the interpretation. Because the square is affecting this negative 4, which means minus 4 times minus 4. If you are imputing it in your calculator, you must put that minus 4 in. You notice that the answer will simply be 16. There'll be no minus there. So I don't know if you can see that from there, right? You can also evaluate it with your calculator from that end. So if you must use this minus in the calculation, remember to put that negative number in bracket before you square, but it's a waste of time. Magnitude is always positive. This minus 4 in bracket raised to power 2 will give you a positive result. So no need of even bothering yourself using that minus. So the magnitude of vector A is equal to, let's evaluate it and see. So we have 5 square, which is 25. We have 3 square, which is 9. And we have minus 4 square, which is 16. So this is going to give us square root of our open bracket. Because I want to press all this term under that square root sign. So I have to open and close the bracket. Since the numbers I have here are being added. So this is going to be square root, open bracket, 5 square is 25, plus 3 square is 9, plus minus 4 square is 16. Close the bracket, equal to. So this gives us 5 root 2. 5 root 2. The knowledge of such would help you out here to know why this is 5 root 2. If you add 25 to 9 to 16, right, you get 50. This term would give you square root of 50. Now, in this 50, the highest perfect square there is 25. So 50 is the same as 25 times 2. So you have the square root of 50, the same as square root of 25 times 2. And if I have square root of 25 times 2, find square root of 25. 25 is a perfect square. So it's going to produce this 5 for you. 2 is not a perfect square. So the square root will still be affecting it. That is how we got this anyway. Now let us move on. If it was the magnitude that you were asked to find, you could leave your answer this way, or you change it to decimal. The choice is yours. I want to say this clearly. When calculating for unit vectors, we do not like this guy to be in decimal. We don't like it. Yeah, generally we don't like it. So no need of changing anything to decimal here. From here, let us now determine the unit vector of this vector. Remember the formula. Unit vector of unit vector is equal to the given vector itself. Since I used A to define the vector, let's maintain it. Divided by the magnitude of that vector, that given vector. So here, vector A as we called it. So I can now fix up the values given here. Let's make use of this part. Okay, let me see. So we have that unit vector A is equal to the given vector itself is 5i plus 3j minus 4k. By the way, remember the name I gave to this vector. When vectors are given with this ijk stuff, right? Or ij in 2 or in 3 dimension. Told you we call it displacement vector. Put the alternative name for that vector. Put it down. Instead of calling it displacement vector, you can also call it position vector. Get used to all these terms. Okay? Because an examiner could use that term. Find the unit vector of the given position vector. This is the position vector. Like here, the one we saw, this is the position vector. You either call it displacement vector or you call it position vector. Then don't forget that the final result, the unit vector we obtain, is also called direction vector. All right, let's move on. We are going to divide this given vector by its magnitude. And what is the magnitude of that vector? 5 root 2. And this is the answer. If your examiner leaves the option, the final answer like this, perhaps in the option, fine, you go for it. Or you can write this as pull out the common denominator, which is going to be 1 over 5 root 2. Open bracket 5i plus 3j minus 4k. Or we could still rewrite the result as 5, watch something now I want to show you, because I want to distribute this 5 root 2 to each of the numerators, right? If I have 5i over 5 root 2, you agree with me that the 5 will cancel. 5 root 2. This and this will cancel. This will now be 5 divided by 5, you have 1. You know that, right? So this is the same as 1 over 2i. So this you're seeing here, sorry, 1 over root 2 rather, not 1 over 2, because there is a square root sign here. 1 over sort 2, or root 2, then I. Let's do it that way. 1 over 2i. I'm distributing the denominator to each of them. I keep saying over 2 over 2. Over square root of 2. Then plus, come to this term, 3 over 5 root 2. There is nothing that can reduce 3 and 5. No common term that can divide them. So you have 3 over 5 root 2. The direction goes with J. That's a. Then we have 4 over 5 root 2. The direction here is what? K. And it is 3-dimensional vector. And of course, any of these could be the answer to this question in terms of the unit vector. If you are asked to obtain the scalar component of the unit vector, all you have to do is to pull out all the scalars here. And what are the scalars? Just this number. 1 over root 2, 3 over 5 root 2, and minus 4 over 5 root 2. Remember, if you are pulling out just the scalar component, you do not add, you do not subtract. Just use comma to separate the scalars. The scalars are all these numbers without the unit vectors ijk, without the direction vectors ijk. So this is how you calculate or determine the unit vector, the direction vector in the direction of any given vector. How about you try this? Remember, when I began this class, I explained by defining unit vector as a vector whose magnitude is equal to what? 1. How about you prove it that yes, the magnitude of any unit vector is 1? I'll quickly use this one to prove it. I'll quickly use this to prove it before we move on to addition and subtraction of vectors in 2 or 3 dimensions. How true is it that the magnitude, the modulus, the absolute length of a given unit vector is 1? Just go ahead and calculate the magnitude and you'll see it yourself. Okay? Let's find out. I just want to prove something. Just want to prove it. Now we have this unit vector to be equal to 3 over 5i plus 4 over 5j. It's a unit vector. That's what we calculated. As a unit vector, we are to determine its magnitude to show that yes, the magnitude of a unit vector is equal to 1. So this is going to be square root. Take this term, 3 over 5 square root plus 4 over 5 square root. Now, if you come to this term, you're going to have, of course, from our indices class in mathematics, you know that this square will be distributed to these terms that are being divided. 3 raised to power 2 will give you 9. 5 raised to power 2 will give you 25. Plus, come to this term, 4 square will give you 16. 5 square will give you 25. Remember what we are trying to do to prove that truly the magnitude of a unit vector is equal to 1. If I do this, please, you go ahead and do for this one. It's still the same procedure. Don't mind the numbers you have there. This will be equal to square root. LCM of this term is 25. Okay? So if you use this LCM to work out this term, this LCM, bring it to the numerator, is going to cancel this denominator here. Now it's the 25 divided by 25, 1 times 9, you get 9, right? It's still the same as taking this 25 up and then divide 25 over 25, you're left with 1 in the numerator, which multiplies 9 to still give you 9. If you do same here, you get 16. 9 plus 16 is going to give you 25, divided by 25, and then 25 over 25 is 1. Square root of 1 is going to give you what? Still going to give you 1. Therefore, we have proven that the magnitude of a unit vector is equal to 1. You can try for this. Use the same approach. Square root 1 over root 2 square plus 3 over 5 root 2 square plus 4 over 5 root 2 all square. Are you getting me right? Solve it and you see that the magnitude will still give you 1. I'm done proving this. This is a proof that the magnitude of a unit vector is 1. I'm going to wipe all these on the board so that we can now talk about the algebra of vectors in 2 dimensions and vectors in 3 dimensions, addition and subtraction. Finish up. Let's check the network situation. So I'll wipe this. We're going to look at algebra of vectors now, vector addition and subtraction. Vector addition and subtraction. Before we move on, let me boost the network a bit. Addition and subtraction of vectors in 2 and in 3 dimensions. So quickly, how do you add and how do you subtract vectors in plane and vectors in space? You know, for a vector in 3 dimensions, usually we use the space coordinates. This is the space coordinate. Are you following, right? I had shown you that one in 2 dimensions. If we give this x, for example, we'll give this axis y, we'll give this one z. If we don't like it, we can transfer this y here and take z up here. Doesn't still matter. Now let us assume that this is the vector. So this is vector f. The direction here, we use I along the x-axis. Then along the y-axis is j. Along the z-axis it is what? K. These are the unit vectors along this axis. This is a vector in 3 dimensions. Generally, can represent the vector in this format. If I say that the vector should be vector f, that is the position vector or the direction vector, should be vector x. Oh no, the position vector or the displacement vector rather, not direction vector. Let's assume that this vector f is now our displacement vector, our position vector, which has these 3 components. Okay, it has the x component, the y component, and the z component. And of course, we expect to have that vector f, its component along the x-axis, unit vector I, plus that vector f, its y component, unit vector j, plus that vector f, its z component, unit vector k. All right, so that's just the whole idea here. For a vector in 3 dimensions, we use the space coordinates x, y, z, you know, at the scalar component values. Anyway, I just have to show you this because I've shown you that one of 2 dimensions. I just hope that power holding company, you know, our power company will not strike now. That's a kind of raining now. Let's check the network situation. Okay, so we are going to move on straight as I'm going to tell you how to add and subtract. You see, if you're adding vectors in 2 dimensions or vectors in 3 dimensions, you take them in order of what I refer to as like terms. You take them in order of what I refer to as what? Like terms. And how do you identify the like terms of vectors? Are you following, right? Simply use their direction vector sign or their unit vector sign. Are you following, right? All this ijk. If you have vector A and vector B and you want to add them component to component, I to I, j to j, k to k. All right, given vector A to be equal to, I'm going to use 3-dimensional presentation of the vector now. Let us say that this is vector ax, that is, this is the scalar component a subscript x. The scalar component of this vector in the x-axis. And of course, you know that the unit vector, direction vector associated with it is I. Then, of course, plus ay, its component along the y-axis. And then plus, of course, you know that along the y-axis, the unit vector, direction vector is j. Then we have az, the unit vector k. This is the z component of this given vector. So given this and another vector b to be equal to, let's say, bxi plus byj plus bzk. If I ask you to add vector a plus vector b, then vector A plus vector B is obtained by adding the components of these 2 vectors according to, like I said, their like terms. And how do you identify their like terms? You use the unit vectors to identify the like terms ijk. So you have I here, you have I here, the scalar component will be added. You have j here, you have j here, the scalar component will be added. You have k here, you have k here, the scalar component to be added. When you are adding, you pick out the common term, of course. The common term here is the unit vectors, ijk, which means if I add this ax, bx, it's going to go the same direction along the x-axis. So you need to attach I to it. Please, let's go. This is going to be ax plus bx, and then I. This and this. Remember, it's simple. Just take them like terms. The like terms. How do you identify the like terms? ijk, simple. So ay plus by, because both of them bear jj unit vector. So ay plus by. And then in the direction j plus az plus bz. Then, of course, you have that unit vector k attached to it. So this is how we add, vectors in 2 or 3 dimensions. If it is in 2 dimensions, one of these direction vectors will not be there. So one of the components will not be there if it is 2 dimensions. Similarly, or also, vector A minus vector B will be equal to, this time around is just to rewrite this same thing, but you are now subtracting. The 2 vectors, you are subtracting them. You subtract and then you sum. This minus this plus this minus this plus this minus this. So we go vector A, component vector A along the x direction minus that of B along x direction or x-axis. Then, of course, we introduce the unit vector I, since the axis there is x, plus do same here, ay minus by, and then unit vector j, plus finally az minus bz. Okay, and then you attach your unit vector k. So this is how you solve them. It's very simple. Addition and subtraction of vectors in 2 or in 3 dimensions. Just 1 plus 1 calculation once the components of the vectors are given to you. Let us take this question, please. Solution question. I'm writing solution. This, of course, is going to be question number, or let me write it down here. Question 3 of our class today. Question 3. Given vector P to be equal to 2i plus 3j minus 4k, and vector Q to be equal to I minus 5j. Good. I've given you this now. Let's see. You see, this vector is in 3 dimensions. This one is in 2 dimensions. Find I. Vector P plus vector Q. And then I vector Q minus vector P. Let us solve this. Let us solve this. So I think I can write my solution here. And it's very simple. If it is in examination hall under CBT case, you don't need to show any working on paper. You don't need to. You can simply handle it directly. P plus Q. This is vector P. This is vector Q. So add them components to components. The I to I, the J to J, the K component to K component. That's it. Like in this case, it's simply, you have I here, have I here. The coefficient of this I, which is the scalar component of vector P along the x-axis, is 2. For that of Q, the scalar component along the x-axis, this I here has invisible 1. So you are adding 2 to 1. Anyway, let's move on straight, please. There is no time. Vector P plus vector Q is going to be equal to, let me just show the working for the first one. When I solve the second question, I'm not going to show the working. You know, plus and minus are handled in a similar way. The only difference is the signs. Are you following, right? Okay, so we go. We are handling the scalar component, or the component of these 2 vectors in x-axis, then the component of the 2 vectors in y-axis, and that in z-axis. Which, of course, you know, this is the x value 2. This is the y value 3. Here, z is equal to minus 4. Here, x is equal to invisible positive 1. That's 1. Y is equal to minus 5. This is a vector in 2 dimensions. So the third component, the z value is not there. It's 0. That is why you're not seeing the unit vector k here. So we go 2 plus invisible 1 here. 2 plus 1. And of course, the direction is given I, since it's along the x-axis, plus the next, the y value, or y component of vector P, which is 3, add it to minus 5. So that's going to give us, 3 plus minus 5. 3 plus minus 5. When 2 mathematics operations of plus and minus are following each other directly, you have to do this concept of plus times minus. When 2 signs are following each other directly, either plus plus, plus minus, minus minus, are following each other? You must do all this plus times minus. So if I have 3 plus, remember we are adding. We are asked to add. So if you pick the scalar component of vector P, before you combine it with that of vector Q, you must to fix your plus sign like I have here. So this is going to be 3 plus minus 5. I've picked the JJ terms, right? The JJ coefficient. And plus times minus is minus. So this is simply 3 minus 5. So you don't go punishing yourself. That plus, minus, all those things are things, you know, little maths that you should work out using the network of your brain. Then finally, plus, we'll move on to the next one, which is minus 4. You know, the z value of vector P, which is in k direction. But if you look at vector Q, that component is not there. Automatically, it is 0. In fact, look at it, I minus 5j. This is the same as plus 0k. Because 0 times any term is equal to 0, it goes off. Okay, so you want to take note, please. when the vector is in 2 dimensions, it is assumed that the third component, its value is 0. So this is going to be minus 4 plus 0. Minus 4 plus 0. It goes with that unit vector I. Good. Plus 3 minus 5. Okay, 3 minus 5 is minus 2. Minus 2, yeah. So plus times minus 2 will give us minus. We'll have 2 in the j direction. And then, of course, minus 4 plus 0 will give you minus 4. Plus times minus will give you minus. You fix your 4 here. And don't forget the unit vector. Okay. And this is how simple. Very simple. There is nothing difficult about it. This is how you add vectors in 2 or in 3 dimensions, as the case might be. Let us now solve the I part of the question. This is I part of the question. I hope this did not cut off. I hope it did not cut off from view. Chinedu, thank you very much. How are you doing? The solution cut off from view a bit, so let me adjust the camera. Let me adjust the camera. Good. Then we'll have to try to round off before rain disrupts the network somehow. So this is Q minus P. That's the next one. Q minus P. That will be equal to, let's go straight on, 2 minus 1 here. The I term, 2 minus 1. 2 minus 1. Let me still show the working here. Then once you're done with that, you add, as you introduce plus. Because here, whether you are doing addition or subtraction, the whole idea is that you are taking an algebraic sum. You are taking what I said, algebraic sum. So by the time you are done with I component, before you move on to JJ, you put plus. Are you following, right? If you are done with JJ component, before you move on to the K unit vector or direction, you still put plus. So we go. The next is going to be 3 minus, no, this y value. Assign the unit vector j. You come here, the y value, assign the unit vector j. 3 minus, this term has minus. So it's going to be 3 minus 5. Once again, 3 minus this subtraction you're asked to do. Then before you bring in the p component, so you have minus 5 and minus 3 minus 5. These will change to plus because minus times minus is plus. So this is going to be 3 plus 5, and then the unit vector assigned to it is j. Then finally plus. It's raining heavily here. We'll go to the last term, which is minus 4. Oh no. What I'm solving is Q minus P. That's what I was asked to solve. And I'm busy solving P minus Q. You see, I've made a silly mistake here. Of course, that's the human part of me. Please, you are solving Q minus P, not P minus Q. I actually wrote Q minus P, but what I'm showing here is P minus Q. Look, and I wrote the P values first before Q. So, oh no, I was scared of this. Please, a moment. Well, it seems like we could still manage that. A moment, let me see. Please hold on. Let me just try to see if I can brighten up here a bit. It's so funny that I was expecting it even earlier before now, but earlier than now. See? Because Let me see. Okay, we're going to manage so that we round off. We're almost rounding off the class. So let us manage. Let us manage the lighting system. So, we are solving Q minus P. Remember, the operation subtraction as a mathematical operation is not commutative. It's not commutative. What does it mean? The order of arrangement matters. If somebody is solving 5 minus 3, the answer is different from 3 minus 5. 5 minus 3, yes, would produce 2. But 3 minus 5 would produce minus 2. 2 and minus 2 are not the same thing. So I could have paid dearly here. Okay. Good enough that I found out. Q minus P, we are taking this minus this instead. Okay. So you come to the I component here, right? The X component in the I direction. Okay. And the invisible 1 as the coefficient of I here, which is the X value, is going to be minus 2. The coefficient of I here. So we have 1 minus 2. And of course, the unit direction I attached to it, plus the next term is that in the unit vector direction J, which of course is the Y value minus 5. So it's going to be minus 5 minus 3. Minus 5 minus 3. Minus 5 minus 3. Remember this middle minus. This middle minus is the operation you were asked to carry out, Q minus P. This is going to be assigned J because it is the Y component, or Y values rather, that you solve for here. And then plus, finally, there is no Z component here. No Z value. No Z value. I told you automatically it means that that value of Z there is 0. Here we have Z value, which is minus 4. So it is going to be 0 minus 0 from here, which is the Z component of Q, minus the Z component of P, which is minus 4 here. 0 minus minus 4. Minus minus is plus. So this is simply 0 plus 4. And then what do you attach? The unit vector K. Let's simplify this quickly. 1 minus 2 is minus 1. So it's meant to be minus 1 and then multiplied by I. And of course, you know that 1, whenever 1 multiplies a term, that 1 becomes invisible. So we just leave the sign there as minus I. Are you following, right? Minus I. Then come to this term. Minus 5 minus 3 is minus 8. So you now have plus times minus 8. Plus times minus is minus. So you fix your 8 there, and then the unit vector J will be attached to it. The unit vector J will be attached to it. And then, of course, finally, 0 plus 4 is going to give us 4. Unit vector K. So it's going to be plus 4 and then K. This, of course, is the value of Q minus P. Answer. So you see that to carry out addition and subtraction of vectors in 2 dimensions, given the component of the vectors, is very simple. It's very simple. Let's take our last question, please. We are, I think, 1 hour gone already. Yes, we are 1 hour gone already. So let's take our last question as we conclude the class. So this is pretty cool. Nothing is there. And quickly, there's something I want to point out to you. I need to point this out to you before we take our next question. Did you observe the answer we obtained at the end of our addition and subtraction, as the case might be? You find out that I, J, K were attached. Those unit vectors, I, J, K, were attached. What does that tell you? It simply tells us that when you are adding or subtracting vectors, your final result is going to be a vector. I repeat, when you are adding or subtracting vectors, the vector result is going to be a vector. So sum of two vectors produces a vector. Difference of two vectors produces a vector. I have a reason why I had to point this out to you, because in our next physics class, which is of course meant to be next week Friday, because this particular class now that is holding was meant to be yesterday, but I wasn't strong at all. I wasn't strong. I was really down, right? Down, stressed. Yeah, I wasn't feeling strong. That's why I couldn't do otherwise. Of course, I have to be alive to keep delivering.